Hopefully this is working. Think so. So hello everybody. We are almost at the point where we can call this the home stretch. So let me just show you where we're at, which obviously you know, but um, maybe it helps to sort of think about we're getting to the last humps, as it were. So we're coming down on the home stretch, which feels good. I know this isn't ideal for anybody. Takes a lot out of me to talk so much twice a week. Um, and no doubt you have to sort of it's a different way of managing your way through a college class to not have the class to show up to and interact with people. So it's hard for everybody. Um, so here we are. We're in the week of April 28th. So we're doing Lab 13. This is about recursion, and this is sort of the lab work this week is looking ahead toward sort of intellectual skills or mental skills that you'll need for the fourth project. So this week's lab won't help you with the third project, but I will be today and Thursday talking about um, going over some algorithms for the third project. Third project is due, well, now that we do Sundays, it'll be due Sunday, May 3rd. And then we'll start evaluating them hopefully on Monday, May 4th. And then we're into the last project cycle for the last few weeks. So that is where we're at. So what I'll do today is part of Lab 13, and then on Thursday I will do the other part of Lab 13, and then about halfway through the broadcast today and on Thursday I'll switch gears and do some Project 3 algorithms and then address Project 3 questions. Don't forget also that I have a question and answer broadcast on Wednesday mornings. That's very lightly visited. Usually there's one or two students in there who get all of their questions answered, so that's a good time to come catch me to get assistance on things like the third project would be during the question and answer broadcast on Wednesday morning starting at 10. Usually I'm on for an hour, but I just stay on until I'm not getting any more questions. So sometimes that's a short amount of time, sometimes a long amount of time. Up to you to choose whether or not to use that. Okay, so we're doing recursion, and I'm just going to throw up some notes. You won't be able to see those yet. All right, so let me throw some notes up to introduce you to the concept of recursion. Um, lecture notes. Today is April 28th, so we're almost to the end of April. Okay, so recursion. Um, in the most, in the practical sense, recursion is really just a function that calls itself to compute a solution. That's all it is. If you've taken calculus, then you've probably uh, you'll see some familiar things. But I'm going to avoid mathematical notation and just talk about it the way that I understand recursion to work, which is sort of more applied and hopefully you'll find practical. But at the end of the day, recursion is simply a function that calls itself to compute a solution. Usually this means that we use recursion instead of using a looping or an iterative, is what we call it, solution. So what you'll see recursive functions do is they'll do some decision making and then call themselves as a part of producing their solutions, but they won't use loops. That's sort of what recursion replaces is looping or iterative solutions. Um, It's not going to feel this way at first, but I promise you when we get to the fourth project, you will find that there are some problems that are far easier to solve with recursion than with iteration. Um, you can try this challenge for yourself when we get into the project 4 cycle. You can try some iterative solutions and see which one you think is easier to work out. But I point that out because recursion um, is just another technique to solve problems. That's all it is. It's a technique to solve problems. It takes practice to do recursion. You have to learn to recognize problems that can be solved recursively, and then you have to learn how to actually build recursive solutions. So it's not easy. And the lab this week is really just a first look to get your juices flowing in terms of recursive thinking. So it's a way of thinking. It's another tool in your toolkit. So and it has to be practiced and learned to do it well. So I try to give you practice. You're going to get lots of practice between here and the end of the semester. Sorry, my voice is already roughed up today. Um, but just be patient because you're going to see me work problems and solve them recursively, and you're going to think, oh, that's simple. And then you could go back to the exact same problem an hour later and you won't be able to do it, at least if you're like me. And I think I'm probably pretty typical. It takes a while to get good enough with your recursive thinking skills to actually apply them to new problems. So just be patient um, and try to recognize when recursion is being used. Um, and I will point it out to you, but generally, not generally, recursion is a way to solve problems instead of using loops. Okay, so to build recursive function, uh, you need two things. Possibly more than that, but let's say that you're at the point where you're making a recursive function, and in the lab this week, I am forcing you to use recursive functions, so that part has already been worked out for you. These are functions that can be written recursively. So if you have to fill out a function that you're supposed to solve recursively, how do you do that? Well, one is so you could do these in either order, but one of the things I usually try to solve first is what's the breaking or the stopping case. Because like loops, if you're not careful, you can create infinite recursion. Just like you can create infinite loops, if you're not careful, you can create infinite recursion, which would be recursion that just keeps going and has nowhere to stop. So I usually try to identify the situation where I want to cause the recursion to stop, just like we do with a loop. When do we want the loop to stop? We call that the break or the stop case. And then two is the identifying how to reduce the problem and making a recursive call. Uh, this is my way of describing this problem. So you have the when do I stop recursing, just like when do I stop looping, and then you also have um, how do I actually apply recursion to solving this problem. And it's usually a matter of reducing the problem down until it cannot be reduced any further. Um, so every recursive call, this is the way I think of it anyway. Every recursive call is built on a smaller piece of the problem. And you keep making the problem smaller and smaller and smaller and smaller until you can't make it any smaller, at which point uh, you should have arrived at a solution. Uh, you do this, by the way, if you've ever I'll show you an example. This is kind of a rough example, but it just occurred to me because I was talking about donuts earlier, and that has made me think about pizza because it was breakfast time earlier, and now it's um, getting closer to lunchtime, so now it's time to think about pizza instead. Let me bring up my camera so I can draw a picture of this. Are you seeing it? Yeah, you are. this would be more comfortable for me. Okay, so here's an example. If you're given a pizza and you're asked to divide it evenly between, let's just say, 8 people, there's a recursive solution to this problem. Um, Now, it's important to note here, by the way, that a piece of pizza with a weird number of people you want to divide it up evenly among is not necessarily a good problem for recursion. But 8 people, if I identify that, oh, 8 people, I can actually solve this recursively. What does that look like? Well, what you do is you identify the stop case. The stop case is when there are 8 slices. That's the stop case. Probably everyone would agree, unless you don't like someone in there, but let's assume that you want everyone to get an equal slice. So the stop case is when I have 8 slices. And then what's the recursion? The recursion is slice in halves. So until we have 8 slices in our pizza, we will slice the pizza in half. Slice it in half, check to see if we have 8. Slice it in half, check to see if we have 8. And we keep doing that until we have 8 pieces. So here's the first call. Right now there's 1 piece. So that's not my stop case, so I will slice it in half. So now I'm going to recurse again on my now kind of 2 pieces of pizza. And I'm going to say, do I have 8 slices? I do not. I've only got 2, so I will slice each of these in half. So do you get that? Actually, 8 is not a good number either, is it? Well, we'll just see what happens. Anyway, so I haven't hit my stop case, so I will slice down the middle again. 1, 2, 3, 4, 5, 6. I've only got 6, so I have to go more. So 1, 2, 3, 4, 5, 6, 7, 8. I've hit my stop case. I stop. So that's just a quick illustration of sort of recursive thinking. You've done this before, I would bet. Or you took the whole pizza for yourself. But you may have thought to yourself, I want to experience 8 slices. Anyway, hopefully you get kind of the basic idea of recursive thinking. And now we're going to do hard versions of it by looking at it in code. And actually, let me leave that up for a second because I'll probably keep drawing pictures. Okay. So I think we're going to work. We'll work 2 or 3 of these problems. I'll check the clock when we get there. Okay, so factorial is it's a classic recursive problem. It's often used to introduce people to recursion. It's probably not the best problem to introduce people to recursion, by the way, because this isn't what it feels like when you do. Don't need to look at that. This isn't what it feels like when we're doing the next data structure on project 4. They're going to feel like different kinds of algorithms, but you can solve this one recursively. And the trick is just to recognize that this is a problem that's solved by a reduction method, and eventually you hit a stopping place. So if you think about, hopefully everyone knows what recursion is. So if I did factorial, I'm sorry. We're talking about factorial. So we can solve this problem recursively, but hopefully everyone knows that 3 factorial means 3 times 2 times 1 is what that means, right? But another way to look at that is that this is really a reduction problem, because 3 factorial is actually 3 times 2 factorial. So I realize that solving a factorial problem is actually just taking a value and multiplying it by the factorial of 1 less than itself, a reduction problem. I can also might recognize here that 2 factorial is actually 2 times 1 factorial. So solving 2 factorial is actually a reduction problem. So you can kind of see that factorial is being called 3 times uh, in a steady reduction. It reduces the value that's being applied, having factorial applied to it by 1 each time. Once you hit 1, that's a stopping case, so you're done at that point. 0 factorial, by the way, is a legitimate value as far as I understand it. That's 1 also. So you could kind of group 0 factorial and 1 factorial as both being legitimate stopping cases. Hopefully everyone kind of sees that relationship. So another way to say this sort of mathematically is that n factorial is the same as saying n times n minus 1 factorial, which we just kind of demonstrated here. All right, so in code, am I overlaying? I'm not. So in code, what does that look like? Well, the stop case, we're computing the factorial of some value here. We just identified the stop case is when the value is, if it's 1 or 0, so I can capture that as less than or equal to 1. Well, that's just 1. So if the value is 1, well, 1 factorial is 1. If the value is 0, 0 factorial is 1. But as we saw in our picture here, those are both stop. Don't reduce, don't recurse. So what do we do otherwise? And I'm going to write this as an else, even though you don't really have to. Else, what are we doing? Well, we have to return the result of computing the value times the factorial of the value less 1. I don't know why I'm pointing at this. I want to be pointing at this. So one thing to note here is that the recursive call is in the return statement, and that's going to be very important for us. I'm seeing sort of crappy video on your end. Hopefully things are acceptable for you. I'm about to do a refresh and see what's going on. Okay, so be on the lookout for this. You're going to see me do it a bunch. I'm not just saying value times factorial, because that doesn't actually have the function return a result. So when you're doing recursion, most of the time you need to be careful and make sure that the recursive part actually returns its result. And then we're going to sort of hand draw this situation here in just a second. But this is recursive factorial. And then I'm going to draw out what it does. So what happens when you do recursion is that the requests for computation kind of stack up on each other. So let's say, for example, I called factorial. And sorry, I'm about to do, well, I'll do 5. Let's do a not too big a one. All right, so I'm going to call that, and I'll just say like sum. That's the sum result equals that. Okay, so what does this look like when it executes? I'm going to draw little boxes and stack them up. So the first time this function is executed, a 5 comes in. So I'll just say that this is when 5 came in. And it's going to wait for a result. So the first thing it does is it checks this value to see if it's less than or equal to 1. It's not. So it returns the value times, and then it calls the function again, which is factorial of 4. So it actually has to wait, because the function got called again. And these requests for calculation sort of stack up, and if you're lower in the stack, you have to wait for things higher in the stack. So this thing is now calling factorial of value minus 1, which is 4, which means that this function is now executing again. And this first execution of the function is now sitting there waiting until the second one finishes. So the second one goes through the exact same process. Is this value less than or equal to 1? It is not. So it goes into the else part and it says, oh, well, I will return 4 times the factorial of 1 less than myself. But factorial of 1 less than myself means that this function is being called again. So now the original call has to wait, while 4 has to wait on factorial of 3. And these are all just sitting there waiting now in the stack. This one's still waiting to hear back from factorial of 4, and 4 is now going to have to wait for factorial of 3. So this function is called value is 3, that's not less than or equal to 1. So it says, well, I will return myself times the factorial of 1 less than myself. Well, now it's waiting. Because now it has to wait until factorial of 2 is finished before it can actually do its multiplication. So factorial of 2. Why is this thing not being... I don't know, maybe I'm shaking the table too much. This is factorial of 2. So now 5 is still waiting down here for 4 to come back, which is waiting for 3 to come back, which is now waiting for factorial of 2 to come back. So this one runs the function. Is this value less than or equal to 1? It is not. So it's going to do a 2 times the factorial of 1 less than itself, which means that now it's waiting, because now this function is just called with 1. So all of these functions are sitting there waiting for the one above them to finish its work. So now 1 factorial comes in as the value that is less than or equal to 1, which means that immediately it starts a cascade. So it's going to say, oh, I got a 1. So now that comes down to 2. So 2 was waiting on factorial of 1, and 1 says, here, I'm done. I have a 1. So now this one's done with its work. Now this one doesn't have to wait anymore because it got a result, and it's going to compute it. 2 times 1 is 2, which it's going to send down, and then it's done. Now factorial of 3 got a result that it was waiting for, so now it can say, it's time for me to go. 3 times 2 is 6. Now it's done. And now 4, which was waiting for a result from 3, now has it. It's going to say, that's 24. And now it's done. And then finally 5 can produce its result way at the very end here, which is what, 120. So now it can say, your original request for a calculation was 120. And now it's done. So that's how recursion works. It helped me a lot to draw pictures like this. You're going to hear me say that for the whole rest of the semester over and over and over again. Drawing pictures like this helped me understand how recursion worked a lot. Just like drawing pictures helped me with singly linked list and doubly linked list and lots of other things. I'm about to test to see if it works, but that's the process. So before I can compile it, I need to stub out everything. So I'm going to go do that real quick, knowing that I'm going to fail tests. So factorial, I think, is done. Fibonacci, though, it's supposed to return an unsigned integer, so I'll just return 0 for now to stub it out. Word is palindrome, returns a bool, so I'll just return false for now. Vector forwards a string, that returns a string, so I'll just return an empty one for now. Vector backwards is string, wants a string, so I'll just return an empty for now. And that'll allow me to hopefully compile. And then I can run the tests and see if I'm passing at least the factorials part. Nope. Yep. Okay, so only have one CPP file. Everything's in the CPP file, so that's nice. I'm going to output an exe file just so I can keep track of where my compiled stuff is. So I want to compile, and then I want to see if I am passing. So lab13.exe, and I'm going to run it with the -s option. That way I can see all of the tests be run, and I can confirm or not confirm that I'm passing the factorial part. All right, so here's the factorial section right here. So I'm passing all the factorials. That's good. Okay, just checking chat, see if anyone has any. Okay, Fibonacci. Let me bring up the browser and just show you how, and remind you that you can look this up. So what is Fibonacci? A lot of you probably already know. For some reason, you get some kind of bike thing here. I think I was looking for bikes, maybe. Anyway, go to Fibonacci number on Wikipedia. Okay, so Fibonacci numbers are a sequence. This is what it's a picture actually, but this is what the sequence looks like. You always start with 0 and 1, and then every subsequent number is the sum of the two prior numbers in the sequence. So you get 0 and 1, and then if you add those together, you get a 1. And then if you add 1 and 1 together, you get a 2. And then if you add 1 and 2 together, you get a 3. 2 and 3, you get a 5. 3 and 5, you get an 8, and so on. And computing a Fibonacci series would be like, give me the 0, 1, 2, 3, 4. Like, give me the 5th Fibonacci number. Is what that would look like. So you have to realize that the thing to recognize is that every Fibonacci number is the sum of 1 before itself and 2 before itself, if that registers. So every Fibonacci number, like 2, is, or any of these numbers, 13 is the result of adding the Fibonacci number 1 less and the Fibonacci number 2 less than itself. Hopefully that makes sense. So that when we go draw it. This is another one. I mean, it's a classic one, so I thought you should see it. What lab are we on? I remember. So I think you should see it because it's expected that computer science students are going to see Fibonacci series and how to compute them recursively. But it's not the best in terms of learning how to think recursively, in my opinion. But still, because it would be expected, everyone in the world thinks that you have heard this, so you should probably have heard it. Hold on, I'm in the middle of thinking. Okay. Where are we? Okay, returns the nth value. So this nth value. We're going to have to find a stopping case here. Oh, I called it the nth value, didn't I? How clever of me. Okay, so recursive means that it needs to be calling itself. It means it needs a breaking case, and it needs reduction, recursive reduction. So let's see if we can find uh, the recursive case, let's just see what happens. We'll experiment a little bit. So if they say give me the 10th, well, that means that I'm going to have to reduce that. So to get the 10th, I need the 9th and the 8th. To get the 9th, I need the 7th and the 8th. To get the 3rd, I need the 1st and the 2nd. So at some point, I'm going to get down all the way. If you think about it, am I still showing my drawing? I'm not. Let me put my drawing back up. So if I want the 10th one, I'm going to need the 9th one and the 8th one and the 7th one, the 6th one, the 5th one, the 4th. I didn't space these out very cleverly. 3rd, 2nd, 1st, all the way down to the 1st one, which is a 0. I know that's a 0. And I know the 2nd one is a 1. I don't remember if that's how I wrote the test, but we'll see. Hopefully that's how I wrote the test. Check and chat. Okay, so let's attack this one and see what happens. So a break case. If we get down, let's see, we need to probably stop too short. So we get down to the 3rd. Well, we can write it this way. If the nth is 0, let's just see if this works. Let's have multiple break cases and just experiment. Is 1. So if we get down to the 1st in the series, well, that's a 0. If we get down to the 2nd in the series, well, we know that's a 1. And then everybody else should be, what do we return? It should be the adding the nth minus 1 plus the nth minus 2. We're going to test it out by hand before we go too far and see if we get the right result. So I actually have 2 stopping cases in this case. If I get the nth is 1, I'm going to immediately return a 0. If I get the nth is 2, I'm going to return 1. The reason why I'm using 2 as a stopping place because I don't have the ability to handle an nth being 0. Now this I may have forgotten how I wrote the test. We'll find out in a second. But my algorithm needs to make sure that we don't go any deeper than, I guess I could say, is less than or equal to 1. Should be 0. But let's just see if this works. I want to use the same piece of paper. I'll fold it and hide that crap. So let's just say the 5th in the series, what's going to happen? So I'm going to get the nth is not less than or equal to 1. It is not equal to 2. So I'm going to end up calling the function twice. I'm going to call it on the fib of 4, the 4th in the series, plus the 3rd in the series. Now I'm drawing this fast, a little bit faster to not just blow the whole hour on this stuff. But hopefully you can kind of see how each step reduces itself. So I'm going to get a fib 4 here, and this picture is going to get a little bit messy, so sorry about that. I'm going to get a fib 4 here, which is going to want to get the 3rd in the series plus the 2nd in the series. Notice, by the way, that this one's in a holding pattern right now. 3rd in the series, the 2nd in the series, so this is going to call the 3rd in the series. This is in a holding pattern. This one's quite a bit harder to draw, so I'm already getting tired of it, in fact. This is going to be fib 2 plus fib 1. Remember, this is which location in the series, so the first in the series plus the second in the series. These two come back pretty quick because the second in the series is a 1 and the first in the series is a 0. So fib 3 is actually 1 plus 0, which is 1. So that comes back right here. I can say, well, that's 1 plus, and then fib 2, which immediately comes back as 1, so that's 1 plus 1, which is 2. So that's here, plus, and then fib 3, we would actually have to go through the stack again, but let's just say that we know that fib 3 is going to come back as 1 plus 0 is 1. So fib 5 is 3. Well, let's see if that is true. 2, 3, 4, 5 is 3, as it is on Wikipedia. So now we'll see if that's how I wrote my tests, because I'll be disappointed in myself if I wrote the test wrong. But let's just try it out and see. Factorial, I failed a fib 1. Fib 1 is 1. Okay, so the test was written with the first in the sequence being a 1 and not a 0. Well, I'm not happy with that. But I'm going to adjust the function to make it work. So fib 1 should be 1. Fib 2 should be 1. Okay, that's fine. But what about fib 0? It doesn't want a fib 0. Okay, we can deal with that. So that was supposed to be a 1. So in other words, we can just simplify this whole thing and say anything less than or equal to 2, let's just spit a 1 out. And see if that satisfies the way I wrote the test. I wrote it goofy, by the way. So it's assuming that positions 1 and 2 are 1. Let's see if that satisfies the test. Okay, so the test expected the first value in the sequence to be a 1 instead of a 0. I have to decide if I want to change that or not, but the point is to pass the test, so... oh, that's right, you can't see the code, can you? Sorry. Okay, so what I've done, I'll go back because I had the code hidden underneath the browser. So I recognize that the test treats positions 1 and 2 as 1s, so I refactored my algorithm to say, well, anything that's 2 or under, I'm just going to return a 1 because that's what the test expected. Everybody else is just going to be computed as the regular Fibonacci number. So that's the change that I made. And that changes because the unit test had a particular way that it was thinking. It was thinking that 1 is the start of the whole sequence. So the nth of 1 is 1, nth of 2 is 1, and then the thing at 3, which should be 2, and so on. But the point here is, and something to be careful of is, when you make a recursive call, you very often need to make sure that you return the result of whatever the recursive call computes for you. So notice that return there on the recursive line. This is the stop or the break case. This is the reductive recursion that's returning the value of recalling the function on a reduction of the problem. So same as we did above, we have a stop case that returns something, and then we have a recursive case that returns a recursive call. I'm going to stop there and shift gears to project 3 so we have time to do an algorithm for that. Plus I'm recognizing that vector forwards a string and vector backwards a string is probably, the problem is probably so similar that once I solve one of them I basically solve both, so those will go fast on Thursday, and then I'll work on the palindrome problem as well. So I'm going to stop on those two, factorial and Fibonacci. I consider those to be the not very useful ways of learning recursion, but those are classic computer science ways of introducing recursion. So there you have it. Now you've had the classic computer science version, and then we'll start using recursion to solve kind of like real problems. Okay, I am going to need this paper, so I'm going to leave my pad out. So anyway, brace yourselves, I'm about to switch gears. So I am going to go open is this where I put it? D-list. Trying to remember where it is. Okay, so I'm back to where we left off with the doubly linked list code, and I'll just sort of review for you where I think we left off. So hopefully that was a quick breather, but I also don't want to make you sit here for an hour and a half if possible. So we're switching gears. So if you need to, if you're sort of working alongside me, I have opened up my doubly linked list HPP file that I left off with on Thursday last week. It's templated. I do not have any includes, which probably it's going to need includes. That's something for you to solve. I have done the constructor. I have left the destructor for you to do because that's pretty simple. We implemented push front, and I drew pictures of that and sort of talked through all of the pointers being everywhere, parts of this algorithm. My hope is that with push front, you should be able to work out push back. It's not as easy as just saying just swap head for tail and tail for head usually, but you've seen the thought process, and the videos are out there so you can go review them if you want. And then last time we did pop back, and with pop back in theory you should be able to implement pop front. And again, you sort of need to work and think through it. Don't just cross your fingers that making tail head and head tail will make it work. In theory it would, but usually people have problems. So just be prepared to have to work through pop front, but using pop back as a reference point. Okay, so I also set up for insert, and this is what I intend to do with the remaining time today, is to work on this insert function. One thing I've done is that I have used my own dang functions to solve a lot of this problem already. So I don't know why that I'm playing with that pen. Where I could to solve insert, I use push front and push back. The whole job of insert is to make sure that a piece of data coming in goes in the right place. I'm going to set up just a little scenario here and kind of show you how insert, push front, and push back don't belong together. Um, but you can use push front for some parts of this problem. So on an empty list, for example, you can just take that value and push front because there's no ordering to do. It's the first one, so just stick it on there. If the value is equivalent to or comes before the value in the head, well, you can just push that one too and still retain the order. So for example, on an empty list, this is head and tail. On an empty list, if I try to insert 20, on an empty list, well, there's no work to do to figure out where should 20 go. I just push front. Boom. Now, if I insert 10, I don't really have that much work to do here either because, oh, well, 10 comes before 20, so I will just hook it up right there. Move head over. If I insert 30, there's not much work to do there either because I can just quickly check, oh, well, that comes after this one, so I'll just put it there. No work to do. Where this algorithm is more challenging is if someone wants to insert something in between. So that's the part of the problem that we're working on today is how do I get a 15 right there? That's where it should go to keep the list sorted. Just like 25 should go in here, 27 would go between 25 and 30 and so on. So when you're doing inserts, the idea is that everything goes into the list in a particular order. So let me draw another picture and just sort of, I'm going to write a whole bunch of inserts. Some push fronts, some push backs. Another push front. So this is always something that confuses people. We have algorithms that can push front and push back, and now we're about to create an algorithm that does an insert. If someone were to use your list in a program, if they start doing inserts, then that is the only way that they should ever put data in there. If they decide to throw a push front in the middle of this, all bets are off. That's going on the front, and that might break all of the pretty ordering that your code did up to that point. So if you were to sell this doubly linked list to someone, you would tell them, hey, if you're going to do inserts and keep your data sorted, don't do push front or push back. Do only insert in that case. But if you need the utility of push front and push back, then my list will also do that. But if you throw an insert in here, it's meaningless. We've already got this. They just kind of went on the fronts and the backs. There's no particular order. So you would tell your customer, you should do all inserts or no inserts, and don't mix the two. Now what they don't know is that secretly some of your insert algorithm is using these, but they don't need to know that. All they need to know is if you start inserting, then you should stick with it. Because if you don't stick with insert, things are going to get out of order. But if you start pushing front and pushing back, well, don't use insert because that's pointless. Things aren't in any kind of order anyway. So this is always causes confusion, but that's the idea. Our list can operate in either of these modes, but it can't mix them without things getting in weird orders. So when I write this insert function, I assume that dummy that I sold my doubly linked list to will only be doing inserts. And if they try to do a push in the middle of that, that's their fault, not mine. All I can do is assume that they listened to my advice and only used inserts, which means that I should be able to know that I can just put these things in order and they will stay in order because I'm only ever going to see this. Okay, so that's the idea. Okay, so now we have this where we want to insert a 15. We've already handled the situation where things just automatically tack on to either end. Because if it comes before or is equal to 10, well, I just stick it on the front and it stays in order. If it's greater than or equal to 30, I stick it on the back and everything's happy. It stays in order. But this is this other situation where I know now it doesn't go before the first one. It doesn't come after the last one. It's going in between two others. So that's what I got to do. And the trick here is to find my spot. So I either need to find a spot where I should come after something or where I should come before something. Doesn't really matter. You can write it either way. I haven't decided what I want to do yet. Well, we'll just see. I'll start writing it and I'll decide. I think what I'm going to go for is I'm going to look for the one that I go in front of. So one whose value, this value is less than or equal to this value is what I'm going to do. Okay, so we're going to do the usual. We're going to start up a marker here. I'm going to call it marker. I'm going to start up a marker here at head, and then I'm going to move it across the list looking for my next after me target node. So else, can you see the code? Yes. So make myself a marker which is pointing at the same thing that head points at. And now I'm going to use a while loop. So while the value I want to insert, that's this value, while that marker's value, let's say, I haven't decided how I want to write this. While my value is greater than the marker's value, that's what I'll do. Let's see how this works. Then I'm going to move the marker over. So the first part of the algorithm is just getting the marker in the right place. So I'm going to start marker at head. And then I'm going to say, while the value I want to insert is greater than the marker node's value, I'm going to move the marker over. So while my 15 is greater than, that's 10 right now, I'm going to move the marker over to the next one. And I immediately find, okay, my value is no longer greater than that. So I'm done. The marker stops. The loop stops. The marker stops. And now I know where I'm going to put my node is in front of the marker. All right, so here's the tricky part. We need to make this node first. So we need to make this node to hold this data. So the marker's in place. Now we're going to make a node to hold the data. So there's this guy. I know, by the way, that these two links to start are pointing at null, which I'm just going to use zeros for now to make the picture less dirty. So here's my new node. Here's my marker. Here's my list. Marker, head, tail. So I need to get this guy hooked up. And the way I do it is I always get the new guy connected before I mess with the old stuff. So the new guy ends next needs to point here where marker is. So ends next needs to point at where the marker is. So that's ends next points at where the marker is hooked up. Ends previous needs to point to the same place where marker's previous points to. So ends previous needs to point to the same place where the markers previous points to. Ends previous points to where marker previous. So here's marker previous is here. So ends previous should also be there. So now the new guy's hooked up. And now I got to mess with these two. One of these is going to be a pain in the butt, by the way. So let's deal with the pain in the butt one last. So markers previous now needs to move down to where n is. So markers previous needs to point at the same thing that n points at. Marker previous points where n points to. So here's n pointing to this node. Here's markers previous also pointing to that node. So now we have that part all fixed up. Now this one. This one is a pain in the butt to get to. So what I'm going to have to do is go to n, go to n's previous, and then from there I can get this next one and move it. So n, go to the node that's previous to it, and then grab its next pointer and move it somewhere. So n's previous's next should come back and point at n. That was hard. But I drew a picture and I just made sure that all of the connections between them had code moving them where they needed to be. So I moved these two. These are now moved down here. I got n hooked up, and then that's it. Except for bumping up the size. Except for bumping up the size. We're going to test this on one more just to see if it works. So I'm going to make a new picture, and let's see if it works. So after that, what we should have, what we should have is head 10, 15, 20, 30, that's tail, head, tail, that goes off into null, null, these are all connected. So this is what we're going to have for a list now. If we were to push, if we were to try to insert 9 or 10, by the way, 9 or 10 will just get pushed on the front to keep it in order. That's great. I don't have to worry about that. If I were to push, if I were to try to insert 30, it would just be connected after the here, or 31. So anything on the ends is already handled. It's the stuff in between that's weird. So let's try and insert 25. So what the algorithm's going to do is it's going to check to see if the list is empty, which it is not. Else if this value is less than or equal to head's value, it's not. Else if this value is greater than or equal to tail's value, it's not. So now we got to get into the list and find our spot. So it fires up a marker. And then immediately starts looping using this value to know when to stop. So if while the value, 25, is greater than the marker's value, move the marker over. Now I'm going to use the pen for the marker. So now the marker's here. And now it asks the while loop question again. Is the value greater than the marker's value? Yes. Move it to the next one. Is the value greater than the marker's value? Yes. Move it to the next one. Is the value greater than the marker's value? No. So the marker stops. Alright, so now the marker stops. The next code is that it makes an N. and puts the value in that node. So here's this new node, n. These are null right now. So let's see, n next, that's this one, equals the marker. That seems good. N previous is the same as markers previous, which is this one. That's good. Then we have markers previous, this one is n. That I like as well. And then we do n's previouses next. This one is n. And that all looks, and we increase the size by 1. So that all looks good. All the pointers got moved around and the new node kind of got linked in properly in the right place in the chain. So that's the insert algorithm. And it's complete. The last one I'm going to do, what I'll do on Thursday, is the remove algorithm. So it would be wise to see how much of these other things, if you're the question asking type, try to tackle some of these other functions so that you have a chance to ask questions about them. And if you're having trouble assembling the application around the file input, make sure you leave time to ask about that as well. Hold on, that's not on the screen very well. Okay, so I'm going to do remove on Thursday. That's another difficult one. But I recommend that you try your best to see if you can get the others functioning. And you might consider writing little tests for yourself. Or maybe find some classmates on Discord and share some testing code with each other to see that your lists work. You can start with the singly linked list tests I provided and adapt them to the doubly linked list code that you've been writing, hopefully. Anyway, that's it. So I will wait for questions before I sign off. Thank you. I appreciate you being here to keep me company. It's if there were no live people in the chat, it would be a lot more depressing. So I appreciate those of you who show up. Yeah, see you too on Thursday. And apologies if you're one of those people who has to sit through 2 of these twice a week. No doubt it's not your favorite thing to do, but we're getting there. We're almost there. You can. Yeah, go ahead and ask. I occasionally have that, and this hard reset thing works for me. Okay, so I'm signing off. I'll be here for a Q&A in the morning at 10. Otherwise, I will see everybody on Thursday. We'll finish what are we on? Lab 13, and then we will work on the remove algorithm. That's the remaining sort of nasty one in the doubly linked list. So queue up the questions, please. Email me if you get stuck on anything. Anyway, so see you next time.